In section 2.3, we'll take a look at functions and relations. The definition of a relation is two sets that are connected to one another. The definition of a function is also two sets that are connected to one another, but in a function, each input is mapped exactly to one output. If we're looking at set, a function from set A to set B assigns each number of the set to exactly one member of the other set. Domain is the set of input values, or x values, in the relation. Range is the set of output values, or y values, in a relation. Below is a picture of a function machine. The way a function machine works is you have an input. So in this case, we're going to input the number 4. A function is performed inside the machine, and then you get an output. In this case, the output is 6. The function that was happening inside the machine was x plus 2. In class on Tuesday, we will take a look at the function machine and try to figure out what the function is by looking at inputs and outputs. So we'll look at this a little bit more on Tuesday. We have 5 ways that we can represent a function. The first way is to look at sets. In our set notation, we could either have it as sets with parentheses and brackets, or it could be sets that we're looking at ovals. In this particular example, we're looking at 2 ovals. In my set here, it looks like my inputs are 1, 4, and 7, and this is my output oval, and its outputs are 4, 7, and 10. We're being asked to decide what the domain and range are in this particular relation. So my inputs are going to represent my domain. So my domain is going to be the set of 1, 4, and 7. And then the outputs represent my range. My range will be the numbers 4, 7, and 10. Then I'm asked the question, is this a function? So for this to be a function, every element in set A needs to be mapped to exactly one element in set B. So 1 is just going to 4, 4 is just going to 7, and 7 is going to 10. So this here would be a representation of a function. Now, if I had a set here that looked a little bit different, if my inputs were 1 and 2, and my outputs were 3, 4, 6, 7, and I had 1 being mapped to 3, and I also had it being mapped to 4, and I had 2 being mapped to 7 and to 6. In this particular case, because my 1 here is being mapped to 2 different values, and my 2 is being mapped to 2 different values, this here would be a representation of something that is not a function. So we'll write over here, not a function. And the reason again is because from this one element we have it going to 2 different outputs. So another way to represent a function is to look at a table. A lot of times we're given a table of values. First up, we're asked to determine what the domain and range is in this particular table. So the domain, remember if we go back to our definition, the domain is going to be the x's and the range is going to be the y values. So here, my domain, my input or my x's will be the set 1, 2, 3, and 4. My range, the set of outputs or my y's, are going to be -2, 1, 4, and 7. Just like with the set, to determine if this is a function or not, what I'm going to do is I want to look at my inputs and make sure that they're going to just one output. So if 1 is my input, it's going to -2. 2 is going to 1, 3 is going to 4, 4 is going to 7. So each of my inputs is going to exactly one output. So this here would be an example of a function. Another way that we see functions represented is using words. So we might be given just kind of a word situation to look at and decide if that represents a function. In this particular case, we have an input is state. So we're going to look at our states. So our input is a state and the output is a capital. So our domain here would just be the listing of states. So here the domain, oops, I wanted to color code it for us here. So here our domain would be the states. We can list out all 50 states, or we can just give a clear description in the domain. So we're going to say the 50 states. And then the range of this function would be the capitals of each state. Now, does this represent a function? Does every state have exactly one capital? So if we went through all of our states, we would see that for each state we have exactly one capital. So yes, this here is a representation of a function. We have two more ways to look at to represent a function. In number 4, we're looking at equations. We can use an equation, can be given to us, and we can determine whether this equation or this relation is truly a function or not. There's two ways to look at it. You can make a table of values and use the table of values to help you with it, or you can make a graph, or you can just identify the type of equation you're looking at. Typically, linear equations will be functions as long as we're looking at linear equations that are not vertical lines. But in this case, let's take a look. We have the equation y equals 2x plus 1. So we'll put in several different inputs or x values. And then we'll figure out what our outputs are. So when I put -3 in here, -3 times 2 is -6 plus 1. That's going to give me an output of -5. If I put in -1, 2 times -1 is -2 plus 1 is going to give me -1. If I put in 0, 0 plus 1 is 1. And then if I put in 1, 2 times 1 is 2 plus 1 more is 3. So I can continue this on. It looks like for every input I'm getting exactly one output. Also, I know I can put negative inputs in and I can put positive inputs in to get my answer. I can also look at the graph. If I go ahead and try graphing the couple of points that I have here, I would see that my graph looks something like this. And so my graph is going to be a line that continues on forever. So this one here is a little bit of a challenge. When we talk about domain, we want to look at all the values that we could possibly enter in. I can enter in negatives, I can enter in 0, I can enter in positives. So when we have a situation where it seems like we can enter in any number, we're going to say all reals is our domain. And then our range, because our y's are coming out negatives and positives, we would say that our range is all reals as well. What it looks like in a graph is it would be an arrow going off in both directions. So I can see that for my y's, I continue to go up to positive infinity and down to negative infinity. But I can also see that my x values, as I'm going up, I'm also going outwards in both directions as well. So that's why I have all reals. Is this a function? We already looked at that. For each x value, we had exactly one y value come out. So we would say, yes, this here is an example of a function. The final way to represent a function is using graphs. With graphs, we would need to identify the inputs and the outputs, or my x's for my domain and my possible y values for my range. In this first graph here, I can look and see and notice that my x values keep going, right? I'm going out this direction. So even though I'm going up, I'm still able to put in x values off to the right. I can still get x values off to the left. So my range here, or my domain, because I'm looking at my x values, my domain here is going to be all reals. My range, though, if I look at my y values and the y values that I'm graphing, I can see that my lowest y value is happening over here at -1, and then it just keeps going up, right? My graph is going to keep going up. So I'm going to say that my range is going to be y values greater than or equal to -1. So my range will be y's greater than or equal to -1. And that's because my graph has a lowest point. Then to test out if I have a function or not, I'm looking to see that each x value has exactly one y value. A quick way I can do that with a graph is I can do something called the vertical line test. The vertical line test says if you draw a vertical line, your graph is only going to cross your line at one point. So here you can see that it crosses at 1 point, 1 point, 1 point, 1 point. So in this particular graph, we are looking at something that is a function. So yes, this graph is a function. If I look at the second graph on the page here, it looks like I have this, we call this a parabola. It looks like my parabola here is flipped over on its side. So again, we want to look at our x values. Notice that I have a starting point on my left. So it looks like my graph is starting here at -5, and it looks like it's going off in the positive infinity direction. So I would say that my domain here, I want to do that in red, my domain is going to be x values greater than or equal to, it looks like -5. So that means I'm starting at -5, and I'm going to be going from -5 to positive infinity with my x's. If I look at the range, my y values, does it look like I have a starting or an ending point for my y's? If I look, I can see that my y's, they started here at 0 and they're going down negative in this direction, and then they're starting here and they're going up positive. So it looks like my range is really going to be negatives, 0, and positives. And when I have a situation like that, I would say that my range is going to be all real numbers. So I can say all reals. The last thing I want to do is test to determine if this relation or this graph is a function or not. And the way that I can do that is I can apply my horizontal line test. I'm going to draw in my horizontal lines, and I want to see if my graph crosses my horizontal line only once. And here you can see that for every line I drew, the graph actually crosses it at 2 different points. So because of that, we would say that no, this particular graph is not a function. All right, let's practice a little bit with what we have learned. We're going to be looking at a bunch of different relations, and we want to determine whether or not the relations are functions, and then we're going to determine the domain and range for each. So in the first example, we're looking at an input of a person. So if we went up to a person and we were to ask them, what is your zip code? Any person we ask would give us one zip code. Typically your zip code is where you live, so excluding college students, you have to change your zip code when you're on campus. Each person has exactly one zip code. So for this here, we would say that this represents a function. And then I can go ahead and say that my domain would be all people, and my range would be all zip codes. All right, let's look at another example. In number 2, we can see that we're looking at an input of month, and the output is the number of days. So if we have a month, like January, does it have just one set of days? So in January, I know the number of days is 31. In February, the days could be 28 or 29, so I have 2 possibilities for February. March, I have 31 days. April, I have 30 days. May, I have 31 days. June is 30. So all the other months except for February are mapped to just one number of days. Because of February, we're going to say that this here is not an example of a function. And the reason for that is because February can either have 28 days or it can have 29 days. And so that's my reasoning for why it's not a function. But even though it's not a function, it still has a domain and range. So my domain would be all months in the year. And then my range of values would be the number of days. So I know I would have 28, 29, 30, and 31 as my range values. All right, if we look at number 3 is written in set notation. Instead of using ovals, we're just using ordered pairs or the coordinates. And so if I go ahead and look at this, an easy way to check is I check my x's. These are my inputs. Each input should have exactly one output. So my input of 4 has 2. Oh, but my input of 4 also has a 3. It also has a 4. It also has a 5. If I was to draw this out using my ovals, this would look like I would have 4 in one oval, and then in my other oval I would have 2, 3, 4, and 5. And then my lines would be 4 is being mapped to all of these different values. So because of this, we would say no, it's not a function. However, it is a relation, and it does have a domain, and it does have a range. The domain are my x values, and in this particular case, my only x value is 4. The range would be my y values, and here I have y values of 2, 3, 4, and 5. All right, let's look at another example. When we look at number 4 here, we're looking at, again, set notation. We have several different ordered pairs. If I look, I have 1 being mapped to 7, 2 being mapped to 8, 3 to 9, 4 to 10. My x values are all different, and they're being mapped to just one y value. So for that reason, I would say that this here represents a function. To find my domain is going to be my inputs or my x values. And so I'm looking at 1, 2, 3, and 4 is my domain. My range will be my outputs or my y values, and those are 7, 8, 9, and 10. All right, in number 5, we're looking at an example in words. It says each dinner is assigned a price. So if we were to go to a restaurant and we were to choose a dinner, does it have exactly one price? Well, that actually depends. Sometimes when you go out to dinner and you order a salad, especially at Applebee's, you have the option of getting the full or the half. So in that particular case, it wouldn't be a function. Other restaurants, it could. So this here, we can say it depends. But we would have a domain. Our domain would be dinner entrees. And then our range would be the prices. And they could range anywhere from $8 to $30 depending on our restaurant. Let's look at one last example here. This last example again is one that's in words. It says each person is assigned a birth date. So if we were to interview people and ask them for a birth date, would they give us just one particular date? Has anybody been born on 2 separate days? Typically when we are born, the doctor will assign the time and date of birth. So because of that, each person will have exactly one birth date. And we can say that yes, this here is going to represent a function. And if we look at our domain, the domain would be all people. And then the range would be all dates. So hopefully you have a little bit of understanding now of what a function is and how it differs from a relation. I'd like for you to go ahead back into Moodle and look for the Nearpod that is labeled section 2.3, checking for understanding, and try some of the problems there to see what you retain from this particular video. Thanks.